We're going to finish up chapter 27, covering the sections 8 and 9. First, just briefly talking about ammeters and voltmeters, and then getting into RC circuits. Okay, so an ammeter and a voltmeter are going to be devices that we're going to use to measure the voltage and the current of a circuit. An instrument used to measure currents is going to be called an ammeter. And it's essential that the resistance RA of the ammeter is very much smaller than the resistances in the circuit. A meter that's used to measure potential differences is going to be called a voltmeter. And it's essential that the resistance of the voltmeter is very much larger than the resistance of any circuit element across which the voltmeter is connected. So how do these devices work? Well, you run a current through an ammeter and a voltmeter, and the magnetic field that is created by the current, which we'll get into in the upcoming chapters when we discuss magnetic field, can actually be measured, and it can deflect a rod or a dial, and that deflection can then could be put on a scale, and you can sort of measure the ammeter or the current and the voltage like that. Okay, so let's get into RC circuits. Now, RC stands for resistor and capacitor, so their RC circuits are going to be a circuit that has a resistor and a capacitor in it. So let's first look at what the circuit would look like. So in the figure here, it says when a switch S is closed on A. So if the circuit is here, which means that this is our circuit around here. Now it wouldn't go up here because there's nothing there, or there's no connection there rather. The capacitor is charged through the resistor, right? So you have your voltage source, your EMF source, then you have a resistor, and you have a capacitor. So this kind of circuit is going to charge up the capacitor. Now when you switch this, when you switch it over to B, the capacitor is going to then discharge through the resistor, right? So if this wasn't connected, but you had this connected, then all you really have is this circuit here, right? And then it no longer goes through your voltage source, so you're no longer adding any charge or maintaining a potential across the capacitor. So then it's going to slowly discharge. And we can sort of, using some equations, we can figure out what the charge is on the capacitor at some specific time, like how much charge is left on the capacitor, maybe after a second or 2 seconds. Okay, so this type of thing is called time varying current, right? Because you have, when you're discharging or when you're charging up the capacitor, your current is going to be increasing or decreasing. All right, so let's first start with the loop rule. We're going to start with the charging up of the capacitor. So we're going to assume that it's connected here at A, and we're going to do a loop roll around. All right, so if we just kind of start over here at the EMF source, and then we're going to go up, so we're going to have a positive EMF. Then we hit the resistor, so that's going to be negative, since we'll say the current is also going in that direction. Right, and then we get over here to the capacitor, right, and that's the voltage of a capacitor is just its charge divided by its capacitance, right? V is equal to Q over C. So we're going to subtract Q over C and set that equal to 0. Now we do that because there's going to be a voltage drop over the capacitor, right? So you're creating your voltage here. There's going to be some drop over the resistor, and then the rest of it is going to drop over the capacitor, right? If you think about a capacitor, you have a positive plate on top and a negative plate. Between those two plates is where the current is dropping, or the voltage is dropping rather. Excuse me, the voltage. Okay, so in this equation, current's going to be a variable and Q is a variable, but they're not necessarily independent of each other. So we know that current is equal to dq over dt. This is one of the first equations that we learned from current. Therefore, we can substitute in for I, right? Substitute into this equation for I. So when we do that, we get R dq dt plus Q over C is equal to epsilon, right, is equal to our EMF. And I just rearranged the equation slightly. All right, so what this is a differential equation. This is a differential equation. Right, we have a derivative term, we have a term by itself. So I'm not going to get into all of the particulars on how we solve this. I'm just going to jump right to the solution, and at a later time we can go over what the solution looks like. So the solution for an equation such as this is going to look something like this. So it's going to be Q, right? Basically, we're trying to find a value of Q that fits this equation. All right, so a value that works is going to be Q is equal to C epsilon times 1 minus E to the negative T over RC. Okay, where R is the resistance, C is going to be your capacitance, T is the time, right, the elapsed time. This E is not the charge of an electron. This E is your exponential E that you find on a calculator. And then you have the EMF and the capacitance. Okay, so this solution satisfies Q is equal to 0 at T is equal to 0, which is sort of our boundary condition, right? At some initial time before the capacitor has had any time to charge, you would expect the Q to be 0, right? So if you had T is equal to 0, this is just going to be, if this term here is just going to be 0, right? And then E to the 0 is going to be 1. So you have 1 minus 1, which is 0, which means your charge is going to be 0. So it meets our boundary condition. That's good. Okay. So what is our current then? Well, we can find our current by taking dq of this, right, with respect to t, right, the equation we just saw earlier. When we take the derivative of this function, we get E over R, or epsilon over R, times E to the minus T over RC. All right, so how do we do that derivative? Well, we know that this first bit here is just going to be a constant, right? So that term is just going to go away. Now, the second term, this C epsilon times E to the negative T over RC, well, the derivative of a value or a function to the an E function to a value is going to be, you just pull this out front and you put it out front, and then you keep the E value the same. All right, so when you pull that out front, you end up canceling out the capacitance, and you end up with an R on the bottom. So that's what we have there. Okay, so how about the voltage, right? So we found the charge, we found the current, we want to know what the voltage is. So the voltage of the capacitor is going to be just the charge on the capacitor divided by the capacitance, right? This is our equation we had up there. All right, so that's equal to epsilon 1 minus E to the negative T over RC. All right, we just took this result and we divided by C. All right, so that gets us what our voltage is. All right, and that makes sense because it's going to be some value of the EMF, some portion of the EMF, right? Because this most likely will be a fraction. Okay. So we can check this voltage real quick just to make sure we're good on that. So we would expect, at some time is equal to 0 for our current to be 0. All right, so let's look at this. Again, if t is equal to 0, this value is going to be e to the 0, which is 1, so 1 minus 1 is 0, so you get a 0 voltage. All right, so we're good there. Now, at t is equal to infinity, we would also expect that the voltage be what the EMF is, right? Because you have this EMF source here, it's going to create a potential across the capacitor at the full value of the EMF. So VC should equal the EMF at t that goes to infinity. All right, so let's look at this. If t goes to infinity, you get a larger and larger and larger value here, and that's going to mean that your E is going to approach 1. This value is going to approach 0, right, because you have the negative in there. So this value should approach 0, which means you have E times 1, right? So there you go. All right, so one final comment about this. Says the capacitor is being charged initially, acts like ordinary connecting wire relative to the charging current. A long time later, it acts like a broken wire. Okay, so we're going to define something called a time constant. Now, the product RC is called the capacitance time constant of the circuit and is represented by our symbol tau, and we usually write it like this. Whoops, let me do that again. Tau looks something like this. Okay, so this tau is going to be the time constant, and it's equal to RC, right? The resistance times the capacitance. Now, at time t is equal to tau, which is equal to RC, the charge on the initially uncharged capacitor increases from 0 all the way to, okay, so let's see what happens. We have our equation, Q is equal to C epsilon 1 minus e to the negative t over RC, right? So at t is equal to RC, which is, again, our time constant, we can go and plug that in. You see that if you have an RC up here, you have RC divided by RC, so it's actually e to the negative 1. Right? So that would be Q is equal to C, C epsilon times 1 minus e to the negative 1. And we can find a value for that. So when you plug that in, you see that e, or the charge, is actually going to be 0.63 times the capacitance times epsilon, times your EMF. All right, so during the first time constant, tau, the charge has increased from 0 to 63% of its value, of its final value, which is going to be C times epsilon, right? So you can have multiple time constants. You can say you could have, 2 tau and 3 tau, and we can see at each of these time constants what we would expect our value for our charge to be, right? Basically, what percentage is of the EMF times the capacitance. Okay. All right, so finishing up, the last topic is now discharging the capacitor. All right, so now we're going to remove it from the EMF source. We're going to close the circuit so that it's just the resistor and the capacitor, which means it's going to uncharge, it's going to give off energy from this resistor. So assume that the capacitor of the figure is fully charged to a potential V0 equal to the EMF of the battery. At a time t is equal to 0, switch S is then thrown from A to B so that the capacitor can discharge through the resistance. Right, so you have some initial voltage which is just going to be the EMF, right? It's the highest value that the capacitor could be, or the highest charge rather, the highest voltage. Okay, so when we're discharging, we're going to have a similar equation than before, but this one, now you'll be setting it to 0. So let's just remind ourselves, let's go back to that. Let's go back a couple slides and remind ourselves what the equation looked like. So we had this equation here where you had the resistance times your change in charge per time, plus charge divided by your capacitance is equal to EMF. Well, when you're discharging the capacitor, there is no EMF because it's not attached to an EMF source, right? So we would just take this equation and get rid of the EMF. All right, so that's going to be your resistance times dq dt plus charge over the capacitance, and you set that equal to 0, right? Because there's no EMF in the circuit. Okay, so now we want to find a solution to this differential equation. And again, without getting into all the details, the solution is going to look something like this. So our charge is equal to some initial charge, Q0, times e to the negative t over RC. Right, similar. So this is going to be for discharging, a capacitor. Okay. And again, we might want to find what your current is for this. So our current is just going to be, again, the derivative of our charge function. So you would take this function and take its derivative, similar to the way we did it before, and you get Q naught over RC times e to the negative t over RC. All right, so that's what our current would look like. And then, of course, if you wanted to find the voltage, we know that the voltage is equal to the charge divided by the capacitance. Okay, so if we look at the graph, what this is going to look like at some amount of time, we can graph the current on one axis and then the time on the other. Right? The current is just going to be the EMF divided by the resistance, or this function here. Basically, we see we get this sort of exponential decay function that sort of has an asymptote at 0. Okay, so again, this is just a quick thing about the figure. This shows that the decline of the charging current in the circuit, the curves are plotted for resistance of R is equal to 2000, capacitance of 1 microfarad, and an EMF of 10 volts. The small triangles represent successive intervals of 1 time constant t. Right? So at 1 time constant, you have this much, which is going to be 63%. Then at 2 time constants, you get here, and then so on and so forth. Okay. All right, so let's finish up with an example. Okay, so discharging an RC circuit. As a car rolls along pavement, electrons move from the pavement first onto the tires and then onto the car's body. This car stores its excess charge and the associated electric potential energy as if the car body were one plate of a capacitor and the pavement were another plate. Right, so they're sort of creating a capacitor right here between the floor and the tire, or the ground and the tire. Now when the car stops, it discharges its excess charge and energy through the tires, just as a capacitor can discharge through a resistor. If a conducting object comes within a few centimeters of the car before the car is discharged, the remaining energy can be suddenly transferred to a spark between the car and the object. Suppose the conducting object is a fuel dispenser. The spark will not ignite the fuel and cause a fire if the spark energy is less than the critical value of the potential energy is equal to 50 millijoules. When the car, in the figure, stops at time t is equal to 0, the car ground potential difference is V naught is equal to 30 kilovolts. The car ground capacitance is 500 picofarads, and the resistance of each tire is R is equal to 100 gigaohms. How much time does it take to discharge through the tires to drop below the critical value of U fire? Okay, so we're really trying to find time here. Right, how long does it take? Now, we can treat the tires as resistors that are connected to one another at their tops via the car body and at their bottoms via the pavement. Right, so if you just kind of think of them as resistors, the bottom of the figure here shows how the 4 resistors are connected in parallel across the car's capacitance. And it shows the equivalent resistance next. Okay, so if you had all the tires, 1, 2, 3, 4, and then you have a capacitor, everything's going to be in parallel, sort of like 2 plates in a way. And then, of course, we can show that the resistance, the equivalent resistance with the capacitor. All right, so first we want to know, well, what is the equivalent resistance, right? We need to know that. So 1 over R, since they're in parallel, we use the 1 over R is equal to 1 over the resistance of the tire, and this is going to be our equivalent, plus 1 over resistance of the tire, plus 1 over resistance of the tire, plus 1 over resistance of the tire. All right, now this, of course, if we take the reciprocal of this when we put it together, is going to be R is equal to the resistance of the tire divided by 4. All right, and we know what the resistance of each tire is, so that's going to be 100 times 10 to the 9th ohms, because it's gigaohms, 100 gigaohms, divided by 4. All right, so that's just simply 25 times 10 to the 9th ohms. Okay. Now we also know our equation for potential energy. That's U is equal to, Q squared over 2C. Right, it's one of our equations for potential energy. So now we want to plug in our equation for Q. Now we are discharging the capacitor in this case, so we're going to use the discharge equation. All right, so that's going to be Q naught times e to the negative t over RC. And this whole thing is squared, right, because of the square there. This is then going to be divided by 2c. We can then simplify that, so we're going to pull out this Q naught squared divided by 2c. That's what I have here. And then all we have left is e to the negative t over RC. Okay. Now I want to get t by itself, right, because we're solving for t. So right now, our value for t is stuck in our exponential right here. So I want to put this on one side by itself, put everything else on the other side. Remember, this is all equal to u. So when I do that, I have e to the negative 2t over RC. Oops, I think I forgot. Yep, let me go back and put in the 2. This is actually negative 2t, because since this is squared, you can distribute that 2 in and multiply the exponent there. All right, so you have negative 2t over RC. And then we can just set this equal to everything that's left, so that's going to be 2u divided by c v naught squared. All right. Now we want to get t alone again, so we need to do the natural log of both sides. So we take this, we take the natural log of both sides. We end up with just negative 2t over RC on the one side, because the natural log of the exponent of something kind of gets rid of the exponent and everything's brought down. All right, so you get negative 2t over RC. That's going to be equal to the natural log of everything that was on the other side, which is 2u over c v naught squared. All right. At this point, we can just go ahead, rearrange. So we multiply our c over to the other side, and we divide by negative 2. All right, so when we do that, we can start plugging in numbers. We have this negative sign up front now. So this is going to be 25. This is going to be our R value, 25 times 10 to the 9 ohms, multiplied by our capacitance, which is given as 500 picofarads, so that's 500 times 10 to the negative 12 farads. This is divided by 2. And then this is all multiplied by the natural log of everything here. So you have 2 times u, which is 50 times 10 to the negative 3 joules, because it was 50 millijoules as given here in the problem. This is their critical value. Divide by our capacitance again, which is 500 times 10 to the negative 12 farads. And then we just have our voltage left, which is 30 times 10 to the 3 volts squared. Okay. Plugging this into a calculator, we get our time to be 9.4 seconds. And there's our answer. And that concludes this chapter.